It can't be. It's bigger than 7, but it's smallest. 看我把没看我把你加上。他的做或者是都对号是零0三，他们那做都没有跟他。因为是他是那个 report 都是那个有点紧迫。我不想给他加。那个的话就理解。
Okay.
That's always 1 because you can make an entry. Yeah, that's a star. Okay, and then IB. And it's got to be the highest. So N/2 of the ceiling. Okay.
How you making out? You got a little quiet. So we're just looking at trees at this point.
N equals 8. Then this would be 8. It would be 8. Would be bigger. Yeah. I just need a flourish. Okay.
Okay, so number 2. Let's talk about this. So the largest value for alpha of G, alpha being, remind me what alpha is? The independence, the vertex independence number. Okay, so it's the size of the largest independent set, and the largest value of alpha of T is, for a tree? N minus 1. Okay, and that only occurs for a star. What's the largest value of alpha prime? What's alpha prime?
Match.
Largest value for alpha prime?
Half of N.
So, half? So in fact, a path, if I choose alternating edges, so the first, the third, the fifth, the seventh, that would give me half. Is it ceiling and floor?
Is that, we were asking, are those the right words to use for that?
Sure.
Okay, so then we said floor on that one.
For the
For alpha prime?
For alpha prime?
Mm-hmm. Yeah.
You sure? So remind me, alpha prime is what?
Matching.
Everybody agree with that? Well, let's look at P13. I think this is 13.
This is 14.
This is 14. P14. What's the edge independence number? 7. What about P13? It's the edge independence number. 6. So it looks like n over 2 is right. Okay, floor function, not ceiling function. Okay, what about the vertex? Let's see. What about the vertex independence number? We got that. What about the cover numbers? So the edge cover number and the vertex cover number.
The vertex is 1.
The vertex cover number can be as small as 1. And the edge cover number?
N over 2.
Ceiling.
N over 2 So when does it hit N over 2? What tree?
Path.
A path. So, and what set of vertices? What?
Which ends
Every vertex?
you choose in a path.
So I'm looking for a set of vertices, a set of vertices so that every edge, so what am I looking for? The vertex cover number. It's the smallest set of vertices, it's a minimum set of vertices so that every edge contains one of these vertices. So it's a minimum number of vertices. So you can't have, we don't want too many duplications, otherwise I'll just take all the vertices. So I'm looking at the vertex cover number. So the vertex cover number, so the minimum set of vertices that cover all the edges.
That's one.
That's one. So what about the
Edge cover.
edge cover? So remind me, what's the edge cover number? Minimum number of edges
Cover vertices.
that cover all the vertices.
So half again.
Half again.
Ceiling.
Ceiling, okay, that's the smallest number. Okay, what about the largest number? One more time. Largest number of, so I need vertices that cover, let's see, so the vertex cover number is the minimum set of vertices that cover the edges. Vertex cover, simply the cover number, so it's a smallest set of edges that cover all the vertices. Smallest set of edges that cover all the vertices. What's the difference in the sizes of those sets? One more time, smallest, so I want a vertex cover number, so I want a minimum set of edges that cover all the vertices. Minimum, smallest set of edges that cover all the vertices.
So is the smallest the n over 2?
N over 2.
The greatest would be n minus 1?
And n minus 1. So what would be n minus 1? The star. So I would have to take all of those edges to cover all of the outside vertices. Yep. Okay. So I want to do one proof. I want to do one proof, and then what I'd like you to do for Thursday is actually work on these problems through problem number 6. Let me back up. A tree, okay, let me back up even further. Forget a tree. What's a bipartite graph? What?
Go for it, right.
Okay, so a bipartite graph is what?
Two independent sets.
So I can partition the vertices into 2 independent sets. So it's a partition of the vertices into 2 independent sets. And in particular, all the edges lie between those 2 sets. Okay. Obviously, if they're independent, there's no edges inside those independent sets. What can you tell me about, let's see, starting with the independence number of a bipartite graph?
The larger of one of those
The larger one of those. So in particular, we know if I have a bipartite graph that the independence number is at least what?
N over 2.
N over 2. Okay. What about the matching number? What can you tell me about, by the way, what's this? Is there, wait a second. So the smallest independent set is N over 2. What about the largest independent set in a bipartite graph?
N minus 1.
N minus 1. Right, so I can go anywhere from, let's say, where each of these are N over 2s, to this one. Okay, so those tell us quite a lot about the independence number of trees, or the vertex independence number. Okay, so that tells us a lot for trees. What about a matching number?
Maximum is 1, and minimum 2.
So the maximum is N over 2?
The minimum is 1.
Is 1, okay. Okay, so wait a second. So here the number of independent vertices is very large, and here it's N over 2. But for the let's see, for the edge independence number, it's very small, and here it's N over 2. So again, there's this relationship. This, I guess I took it away. There's this relationship. Okay, hopefully. So here's what, without looking in the book, could you prove that this was true? One more time. What's alpha? So that's the independence number, and this is the
Vertex cover.
vertex cover number. Can we prove that alpha plus beta is always equal to n for any graph? So let's see. What is the vertex cover number? Give me the definition of the vertex cover number. It's the
Smallest number of vertices to cover the edges.
okay. So so let's choose an independent set. Here's an independent set, and it's as large as possible. Alpha vertices right there. Here's beta vertices. Sorry, here's the rest of this is n minus alpha vertices. It's just not moving. Okay, one more time. Here's alpha vertices. Here's n minus alpha vertices. What can you tell me? Is n minus alpha is it an edge cover? Is it let's see, these n minus alpha, are there any edges that aren't covered by these n minus alpha? No. Okay, so all the edges either are in here or over here. So this is the edge cover number. So this number of vertices covers all the edges. So again, that essentially is the proof that alpha plus beta is n. When I take a largest set of independent points, then what I have, I know that every edge is covered by this set of vertices. This set of vertices covers all the edges. Some of them are covered twice, which is okay. Which edges are covered twice? Maybe there are no edges. This is not necessarily a bipartite graph. When I say covered twice, I mean both vertices. So if there's an edge down here, that edge is covered twice, but that's okay. It's covered at least once. And any edge between these is covered at least once. So this is the edge cover number. This is the vertex independence number. So we have this nice relationship between alpha and beta. Alpha plus beta is equal to n. And hopefully we'll start on Thursday, I would like you to think about, how do I prove that alpha prime plus beta prime is equal to n? Okay, so you have the definitions of what alpha prime and beta prime are. Now can you show that that sum is equal to n? It's a very similar proof as this. Take a set that meets alpha prime and show that what's remaining is beta prime. Okay, and that's where we'll start on Thursday. Okay, questions? Again, I took chapter 7, and I put those definitions all in one place. You guys have them here. They're also on Canvas. I want you to continue to work on, I want you to continue working on this, as well as up through problem number 5. I actually want 6, but let's start with, so we've done 2. I want you to look at 3, 4, and 5. And that's where we'll start on Thursday. Okay? There is a homework assignment. Yes, it's in Canvas. Yes, okay, yes, okay, I'm sorry. Okay, there is a homework assignment that's due next Tuesday, May 7th? That went live this morning, I think.
Oh, do we really?
All right, we'll see you Thursday.
PowerPoint reviewers.